Of course, of course.
Let's move. Next is Aaron Valdez.
Okay, so let me start. Okay, so today I'm going to be talking to you about optimized multi-layer structures with phase change materials. My name is Aaron, and my mentor is Dr. Verones. So, have you guys ever wondered how privacy glass works? Well, it all boils down to the idea of switching the transparency of the material from transparent to opaque when you apply an electrical voltage across them. And the most common material for privacy glass is PDLC, which stands for polymer dispersed liquid crystals. So, how does all this stuff that I just mentioned related to optimizing multilayer structures? Well, the simple answer is that on our research, we try to come up with combinations of multiple phase change materials as a way to obtain the biggest difference in absorption. Why are we looking for the difference? Well, as seen in this clip from the privacy glass, the material is able to change its absorption from probably 20% to 100%, which means there's an 80% difference, probably turning from 20% to 100%. So, as you can see from this diagram over here at the bottom, the phase change materials that we are mostly testing is GST, which stands for germanium antimony tellurium. The main groundwork that has been done in this project was done by graduate students of Dr. Verones, which created a program which is able to not only find the most optimal thickness, but also the optimal combination of material and thicknesses to obtain near perfect absorption. This was done via hybrid optimization algorithm coupled with the transfer matrix method to optimize material composition and the layer thicknesses of the aperiodic multilayer structures. This innovation led to the previous REU student to expand its application. He worked on optimizing their absorption ratio in multi-layer structures when GST switches between its crystalline and amorphous phases. This is where I came in. My first step in this project was simply being able to run the original code in the HPC computer and see if my results matched the work of previous students. Next, I created a method to obtain two optimized results for both scenarios, a crystalline state or amorphous state. Then I have to implement a fitness function which will obtain the maximum of the difference between the absorption of the crystalline state and and the, the amorphous state. Finally, my last step was to run as many simulations as possible to see a pattern and test the accuracy of our data in place of the physical experiments that we would do. Here's the latest simulation of a 5 multi-layer structure run by me, and here's a simulation of the original paper with 5 multi-layer structures. As you can see, the spectrums are the same. Here we can observe the material composition and the layer thicknesses are the same, which means that my results are consistent. So to finish the previous work, I created a function that converts all multi-layer structures with GST of any type into either only amorphous or only crystalline. Then I devised a fitness function to observe how well each multi-layer structure performs based difference, on their difference and their in the ratio of absorption. So the strategy to convert multi-layer structure with GST of any type into either only amorphous or only crystalline ones is by swapping all GST crystalline layers with GST amorphous layers or vice versa. As seen in this code, we first find the material ID of GST amorphous and then we iterate through all the layers, switching those layers that have crystalline with amorphous. Then as you can see, we find all the GST crystallines and finally we just swap them. And it works in the same manner when switching from amorphous to crystalline. The difference in this function. As in this code, we first convert original multi-layer structures into two new multi-layer structures consisting of either only amorphous or only crystalline. Then we simulate each of those new layers that we created. As you saw from the previous slide, this is a result of the simple conversion of our current multi-layer structure to two different multi-layer structures made of either only amorphous or only crystalline. Next, we have to simulate each of those new multi-layer structures created. As you can see by the result 0, it will be the result of the simulation, and result 1 will be the result of the simulation of crystalline. This simulation uses a fitness function that iterates through all the specified wavelengths, find the maximum absolute difference of absorption between the two phases. And as you can see, we actually find the maximum absolute difference of the absorption of the crystalline state and minus the absorption of the amorphous state for all the wavelengths. And by the way, 500 here is an arbitrary value for maximizing our results. So the ratio fitness function. This fitness function is similar to the previous one, except that we're looking for the ratio of absorption. More specifically, we're looking for the maximum ratio of absorption of crystalline over the absorption of amorphous across all wavelengths. And here I'm going to describe the fitness function, which is basically we iterate through all the wavelengths, then use a comparison to get the maximum, and finally here we are using arbitrary values to be able to maximize our results. So yeah, and as you can see, our main goal is the ratio fitness function is to obtain the maximum ratio between the absorption of the crystalline state over the absorption of the amorphous state for all the wavelengths. So for the simulations, there were two phases for the simulation. First, testing the code. This was to see if the result is consistent. The second phase was obtaining results of fitness functions for the difference and ratio between amorphous and crystalline. Are the results consistent? Well, yes. For the difference fitness function, you can see that all the spectra are identical, which means that all results are consistent. The same happens with the ratio fitness function, where we're also able to obtain the same spectra for the same amount of layers, which means all results are consistent. Difference fitness function, relevant results or optimal results. In this chart, we can see how increasing the number of layers increases the difference in absorption between amorphous and crystalline. As you can see, there's a visible difference between having 2 layers and 7 layers. In this graph, I present the most optimal result with 0.65 difference in absorption. This was obtained with 15 million trials for 2 layers. By the way, these are preliminary results because most likely the optimization algorithm has not converged for structures with large number of layers. So what do these preliminary results mean? In a way that the results we see is transition, it can be a transition from here, from 20% all the way to 80%, given the fact that we have a difference in absorption of 0.65, which in a sense can be like a 60% difference in absorption. So it could be a difference between going from 20% all the way to 80% in absorption. For the ratio fitness function, so this chart demonstrates the increase in ratio between the absorption of crystalline and amorphous structures resulted by increasing the number of layers. This is the most optimal result produced by the ratio fitness function. The maximum ratio obtained was 6.64, which meant that the absorption for crystalline structure was 6 times bigger than the absorption for amorphous structure. Furthermore, this combination had the maximum difference of 0.66, which is the highest absorption difference we have ever obtained. So to conclude, given the fact that these are preliminary results, we still need to run more simulations as a way to obtain the highest difference in absorption between the two structures as a way to obtain the best combination of materials and thicknesses. And thank you, Dr. Barones, and this is all thanks to the National Science Foundation.
Any question or comments? So when I have a question. I mean, you focus on a large range of wavelengths. Is all the visible range the one you want to I mean, in all your figures, all your plots, you have wavelength on in the horizontal. So your optimization is for a range of wavelength for a
No,
given.
it's a range of wavelengths. Like, yeah, it's